formation of massive black hole seeds through Hoyle-Littleton Bondi accretion of self-interacting matter, and we consider the seed to be a moving seed. So first I would like to talk a little about the problem, what the problem is. We all know the existence of very massive quasars at the early universe, and these quasars hold very massive, supermassive black holes to be precise, at its center. Now, the main question is how these massive black holes come into the picture at such an early phase of the universe. That is what the basic idea of my problem is, the formation of these massive black holes. Now, we will consider the formation of these black holes from seeds and look into how these seeds will form. Now, there are various possible mechanism of formations. I think the whole thing is not visible. The whole thing is not visible. So there were various mechanisms of formation considered yet. Some of them were collapse of very massive stars to form massive seeds, then mergers of stellar mass black holes to form intermediate mass black holes. So I had 4 of them listed here. Unfortunately, the slide is not built properly. Now, my problem is I will consider the formation of intermediate mass black hole seeds by the accretion of HLB model onto a stellar seed of 20 solar mass. Now, in this HLB model, this is a classic work of Bondi that he said that the accretion would be somewhat sort of a quasi-spherical accretion, and the accretion rate is given such, which would depend on the sound speed in the accreting medium and the density of the dark matter fluid. Now here the accretion is not accretion of normal baryonic matter, it's the accretion of self-interacting dark matter. It's neither cold dark matter. We consider our dark matter to be particles which are interacting among themselves. Now, according to Bondi's work, this type of accretion will continue till a time when the accretion radius will be equal to the mean free path of the self-interacting dark matter particles, which gives us a relation between the accretion radius and the mean free path of the particles. So if we insert this into the rate equation, we get how much the black hole would grow till that time for a particular range of cross-section of the particles, the mass of the particles, and the sound speed of the medium. Now, we consider a range of the cross-section of the dark matter particles. We consider from 0.1 to 5 centimeters square per gram. Now, the reason is that 0.1 centimeter square per gram is capable of reproducing core densities of clusters, low surface brightness spirals, and dwarf galaxies. Then a range of 0.5 to 5 centimeters square is required for the mass profiles that have been observed, and then also the survival of galaxy clusters constraints that sigma by MDM has to be less than 1 centimeter. So we took the entire range and tried to generate the seeds within the range of these values of the sound speed. Now, why particular these values of sound speed? If we consider the ambient temperature of the medium to be around 10 to the power 4 to 10 to the power 7 Kelvin, then the sound speed comes up to be this much. There is a relation of sound speed. I am sorry, I didn't display that here. There is a relation between the sound speed in the medium and the temperature of the medium. So within the value of sound speed and within the range of sigma by MDM, we have generated seeds within the mass range 10 to the power 3 to 10 to the power 8 solar mass. Obviously, for larger range of sigma by MDM like 5, 4, we will get much larger seeds, 10 to the power 9 and 11, but we ignored that. Now we have in these seeds formed at time t dash. What we will do is, we will try to see what is the nature of our seeds now. We divide the entire system into 3 regions. One is the mean free path of the self-interacting dark matter particles is much greater than the gravitational scale height. The second is the mean free path is smaller than the gravitational scale height, and next is the transition region. The long mean free path region is actually the extended halo, and the shorter mean free path is the fluid-like inner core. Now, I am sorry, this is a mistake. This should have been the inner core, and the shorter mean free path is actually the extended halo. I'm sorry for that. Now, for the fluid-like inner core, if our black holes need to be of fluid nature, that is the inner core of the halo, then it should satisfy that the mean free path of the particles from which the black hole form, it should be greater than the gravitational scale height. So, now we have an inequality which gives us a minimum limit of the halo density. If we insert the parameters sigma by MBM that we have used before, the velocity dispersion is less than 10 to the power 7 centimeter per second. That is what matches with numerical simulations and observations. Then the central density is taken to be 0.02 solar mass per parsec. Now these values give us this. If we insert the central density and velocity dispersion, we get these minimum densities of the ascidium halo. We will compare this with the black hole density, since we have formed the black hole of the mass just before. Yeah, we have the black hole masses here. So now we will compare this ascidium halo density with black hole density that we have found. For the range of black holes that we found, the black hole density comes out to be around the displayed values. So if we compare the black hole densities now with the ascidium halo density for a particular value of sigma by MDM, that is a particular range of particular value of the cross section of the dark matter particles, we see that the black hole density is larger than the halo density, which is quite what we needed to justify that our cores, that our black holes that form, that are of fluid nature. So the cores that we obtain now, they are fluid like, and so the fluid model, we can say that the fluid model preserves its characteristics for the this should be longer mean free path region, I'm sorry, that is in the inner core region. So we have generated the seeds, we have said the nature of the seeds. Now moving forward, we have formed the seeds. At the first place, we consider the seed to be formed from a 20 solar mass black hole. Now what we will do is, we will see if this, what about this 20 solar mass black hole? How will it be in the halo? So in order to do that, we calculated the dynamical friction time of this 20 solar mass black hole. We say that if the 20 solar mass black hole is suppose moving in the halo with Ri with the initial radius at time t is equal to 0 from the center, then sigma b the cross section of the dark matter particles, and mhb will be the mass of this black hole. So if we insert these values, then we get that the dynamical friction time is much larger than the Hubble time. That means the black hole cannot be stabilized in the halo, it needs to keep on moving. So the seed cannot be stabilized even in the presence of dynamical friction. So it will start to move through scattering other stars and dense gas clouds. So we consider that the black hole will move supersonically, since our maximum sound speed was around 100 km per second, this one. So we consider that the black hole, suppose the black hole mass is of the 200 km per second. We actually took a range for it greater than 200 km per second, but I'll explain why we neglected the higher velocities. Now, if we insert this velocity into the original rate equation given by the work of Bondi, the rate equation has now a new term v along with the sound speed in the medium. So now we have got the rate equation, we have generated those seeds. The interesting thing sitting here is rho s, that is the density of the dark matter that we are considering. Now the dark matter that we are considering, ascidium, self-interacting dark matter, we can consider different profiles for it. Here we have taken NFW profile, that is the Navarro-Frank White profile of the dark matter. There are other also profiles like singular isothermal sphere. So that didn't give us quite sufficient results. So we stick to NFW profile. Now within the NFW profile, the density profile is given such where RA will be the accretion radius, RC, rho c are the critical constants, and alpha is the asymptotic slope. Now previous observations, they say that alpha needs to be equal to 1 to match with the observations. So if we take alpha equals to 1 and insert it into the rate equation, we'll get an idea of how much time the black hole will take to form from a 20 solar mass to our range. That was 10 to the power 3 to 10 to the power 8. This is what we obtained, and 20 solar mass was the seed that we considered. So from 20 to 20 solar mass to say 10 to the power 3 solar mass, the formation time scale would be such 463 million years around, and the higher seed would take around say 2 million years. Now this is something different. Say the larger seed is taking quite shorter amount of time, whereas the smaller seed is taking much longer amount of time to form. Now one possible explanation could be that it is very hard to stabilize the smaller seed in the halo. It will suffer frequent collisions, scattering, and it will accrete at a lower rate compared to a higher rate, which will be much more stable in the halo. So these are the time scales that we found. These are the time scale that we found that the seeds would take to grow into an intermediate mass black holes. Also, we took alpha less than 1, 0.75. 0.75, I just displayed the lowest seed, the time for the lowest seed and the time for the highest seed here. Now see, this time for the seed range is of the order of few gigayears, which is quite large. So it is, now we can conclude that within the NFW profile alpha, the asymptotic slope equals to 1 would be more applicable to generate seeds or say intermediate seeds for supermassive black holes. Because we even check for values lesser than 1 such as 0.5 and 0.2 that would give rise to seeds within a time scale of few thousand gigayears, which is not feasible. So that's why we excluded the lower values of alpha and we stick to alpha equals to 1 to generate our necessary seeds for supermassive black hole. So this was one process of generating the seeds for supermassive black hole, considering Hawley-Tilton-Bondie accretion of dark matter, self-interacting dark matter to be precise. The other process is gravothermal process. I'll go brief about it. Gravothermal process is what, in simple picture, we have a halo of say self-interacting dark matter particles. It's similar to what globular clusters experience. Since it is a self-gravitating system, in virial equilibrium, it will start to collapse because it has a negative heat capacity. If the halo has a slightest, say if the core of the halo has a slightest specific heat difference with the halo, then the energy transfer would then increase. The core would lose its energy and also increase its temperature, just like the basic thermodynamics. So in that process, ultimately it will start losing energy and it will again increase its temperature, the core of the halo. In that process, the core will infinitely contract to become ultimate relativistic, and then it would collapse to form a black hole. That is one simple idea. So in gravothermal collapse, we have loss of particles because the collapse happens and the particles are lost and we have a smaller cross section of the interacting dark matter particles. So at a time the heat conduction by the particles will stop. Also the mass will be reduced, and now we have a very finite mass concentrated in a very small volume and at a very high temperature. This will give rise to secular instability. Now secular instability is not favorable for producing very massive black holes. So suppose we have a large cross section of the dark matter particles, which means that we have small cross section. In that case, the mass loss will stop at a time and the core will collapse to become relativistic. That is what I said before, and this will give rise to dynamical instability. So the whole core of the SIDM halo will collapse to form intermediate mass black hole. This is one process of generating massive seeds through collapse of SIDM halos. Now we calculate, this was just theory. To prove it, will it collapse? We calculated the dynamical time scales and the collapse time scales. The dynamical collapse time scale is what we know as 1 by root over g to the power rho, within which it will react to any sort of gravitational instability and start collapsing. Now, just like we took the central density, rho c 0.02 solar mass per parsec, the dynamical time scale is about 100 million years. Now, the thermal relaxation time scale, that is the mean time between the collisions, it is given by this relation. So, if we insert the values of sigma by m, rho from here, then we get the thermal relaxation time scales of few hundred to 1,000 million years. Now, the gravothermal collapse time scale is the lifetime of the core until it collapses. Basically, at what time the core will come at a stable position. It won't collapse further. So we calculated the core collapse time scale, and we see that the dynamical time scale is much smaller than the collapse time scale, which was about 100 million years. So it is justified that yes, an acidium halo can dynamically collapse to form a black hole, since its dynamical time scale is much smaller than the collapse time scale given for the values of central density and within the range of cross section. So we conclude that the central region can collapse under dynamical instability and will produce a seed black hole. The seed black hole can now stay stable inside the halo, and it can start accretion from the surrounding. So yeah, that's it. Last, I want to talk about the future prospects. The first thing is that in this whole process we considered not just cold dark matter, we considered self-interacting dark matter. Now that could be one good thing, that because self-interacting dark matter concept is applicable in lower scales to match the flat density profiles of low surface brightness galaxies and dwarf galaxies. So in that case, we can consider a new model of dark matter where the dark matter particles are not cold and they are instead self-interacting. Then the next could be that the future observations of seed black holes at high redshifts through gravitational waves would suggest us how massive the black holes were formed and what redshifts were there from. Could they have been potential to be the seeds of supermassive black holes at early phases of the universe? And next, the halo properties to host these kinds of seeds. To host these kinds of seeds means to have such density profiles, to have such values of sound speed, everything. The halos should be, or the galaxy mass is related to the number density of observed quasars. If we have an idea of how it is related, and is it that the black hole can form under those considerations, then it would be a profitable thing for the future. That's it. Thank you. These are some of the references.
Okay, thank you for a nice presentation. It's now open for discussion. Yes.
So you talked about the sound speed. So is it a parameter or does it come from an equation of speed?
Here I haven't displayed, but it is related to the ambient temperature of the medium itself.
It comes from the temperature.
Yeah.
The temperature thing.
So we took the ambient temperature to be around 10 to the power 4 to 10 to the power 7 Kelvin of the whole medium, a range. Within that range, we obtained the sound speed to 10 to 100 km per second.
Any more?
How is this self-interacting dark matter different from ordinary dark matter?
Oh, ordinary dark matter, it's not reacting, right? The dark matter particles which constitute the cold dark matter, that it doesn't react with it. Here we have a cross-section term present here because we consider the dark matter particles to be having subsequent collisions enough, which does not have a negligible effect. We will consider the effect of their collisions in the process of studying the objects in a self-interacting dark matter halo.
Any more? If no, I want to have few questions. Okay, question number 1, you already mentioned gravothermal collapse dynamics. So is there any threshold condition for gravothermal collapse dynamics to occur?
So the core which will start to collapse, it has to be at a higher temperature than the surrounding. That will initiate the gravothermal collapse. The core will, it's the basic thermodynamics, the core will start to lose energy to be in a thermal equilibrium. It starts to lose energy, but it gains temperature. In a way, it gains temperature, and as a result of it, there is a time comes when the particles in the core itself starts interacting very vigorously to form a compact object. It collapses until
Okay, there you also mentioned secular kind of instability.
yeah.
What is that secular instability in this context?
Okay. Secular instability. Okay, I'm not very I'm new to this topic, secular instability, so I don't have a very clear picture of it. I will try to explain. Secular instability is it's some sort of a condition that won't give rise to a massive black hole. It will somehow halt the process of collapse of the cloud. That is the least amount of knowledge I have right now. I'm sorry.
Okay, just last question. So there are enough literature wherein dark matter is treated kinetically
Yeah.
and sometimes again by fluidic approaches, right?
Yeah.
So under what condition you are going to consider kinetic model or sometimes fluid model? So is there any justification for you? You have mentioned only dark matter as fluid-like.
Yes. Yeah, we consider.
Yes. So what is the physical basis regarding this? Which approach to apply and under what condition?
I have to look into that, sir. I am sorry.
Okay, thank you. Okay. So let us thank the speaker once more for wonderful presentation. Now it is next.
We have a small announcement.
Okay, thank you, please.
Tea is ready. So let's have a small break and we'll continue the session after 15 minutes.